All right, today we are diving into one of the most powerful and frankly coolest ideas in all of programming and logic, dependent types. Now, this isn't just about writing code, it's about embedding mathematical proof right into your programs. So how in the world is that even possible? Let's find out.
I mean, just think about that for a second. What if you could write software where entire classes of bugs are, well, they're just impossible to even write in the first place? Forget hunting for them later. This is the radical promise of dependent types. It's about building software that's fundamentally more reliable, more robust, and just more trustworthy right from the very beginning.
So how do we get there? How do we actually achieve this promise of self-proving code? Well, it really requires us to flip our whole way of thinking about errors on its head.
You know how it usually goes, right? For decades, we've had this write-then-test model. We write all our logic, and then we write a completely separate pile of tests to try and poke holes in it. And look, it works, kinda, but you're always playing catch-up. Dependent types they flip the script. The goal is to make the type system itself so smart, so expressive, that a program with a logical flaw won't even compile. The proof is in the programming.
Okay, so what's the magic trick behind all this? It really boils down to one single core concept. What if types weren't just static, boring labels? What if they could actually depend on the values running through your program?
And that's it, right there. A dependent type is simply a type whose very definition changes based on a value. And this incredible idea isn't new, by the way. It comes from the foundational work of the logician Per Martin-Löf way back in the 1970s. He was the one who first really built this deep, powerful bridge between the world of logic and the world of programming. And this is where it all clicks. Let's make this real. On the left, you've got your standard list of integers. Your type system knows it's full of integers, sure, but it has no idea how many. 0? A million? It doesn't know. But look at the right. A vector's length, which we'll call an n, is baked right into the type itself. This means if you write a function that needs two vectors of the exact same length, you're guaranteed to get them. If you try to pass in vectors with different lengths, your code won't even compile. Boom! An entire category of bugs just vanishes.
So you can see how encoding properties like length into a type isn't just some clever little trick. It's the foundation of a whole new paradigm, programming as proof. When your types are this smart, your code literally becomes a verifiable mathematical argument.
And this is where things get really ambitious. Using these ideas and tools called proof assistants, researchers have done some truly incredible things. They've actually formalized entire branches of mathematics. They've essentially taught a computer the foundational rules of set theory and then used it to build a machine-checked, provably correct version from the ground up. It's wild.
And listen, this isn't just some academic thought experiment. There's a whole ecosystem of real-world tools out there like Coq, and Isabelle. These proof assistants are used every day, both in universities and in high-stakes industries, to build software that is mathematically guaranteed to do exactly what it says it will do.
The implications of this are they're massive, and they touch on fields that go way beyond just checking software for bugs. Let's just take a quick tour of where this is all going.
So the first big one, as we've seen, is in mathematics itself. It lets mathematicians build proofs that are so intricate and complex they would push the limits of what a human mind can even verify, but they can be checked by a computer with absolute total certainty.
But it's also being pushed to the very frontiers of physics. Think about quantum computers. They operate on these bizarre, counterintuitive rules. For instance, you can't just copy a quantum state. It's forbidden by the laws of physics. Well, by encoding these physical laws directly into the type system, we can make it literally impossible to write a quantum program that breaks the laws of nature.
And what's more, dependent type theory is so fundamental that it can act as a kind of meta framework, a tool for creating other logical systems. Think of it like a programming language for designing new kinds of logic. It lets us build these custom rule sets for really specialized problems, all inside one unified, verifiable structure.
And the field just keeps on evolving. Newer ideas are finding even more powerful ways to reason about what it even means for two things to be equal. And that seemingly simple question, well, that leads us right to the next great frontier for this whole technology.
So where does all of this ultimately lead? It leads to one of the most beautiful and, frankly, mind-bending ideas in all of modern logic and computer science, homotopy type theory. Okay, so homotopy type theory, or HOT for short, proposes this incredible new way of looking at things, pioneered by the Fields medalist Vladimir Voevodsky. It asks us to imagine that types aren't just containers for data, but that they are geometric spaces. The values inside those types are points in that space. And a proof that two values are equal, that is literally a path connecting those 2 points.
This is the profound idea at the heart of it all. Logic becomes a form of geometry. Proving theorems becomes the same thing as exploring the properties of shapes. And this connection, it reveals these deep, totally unexpected structures that link the worlds of programming, logic, and topology.
And that kind of leaves us with this final thought. We started this journey with a very practical goal, making our software more reliable. But the path has led us to this place where code and proof and geometry are all just different ways of looking at the same underlying truth. It's a stunning new perspective, and the worlds that it's going to let us build, well, we're really only just beginning to explore them.